Hello everyone, welcome to GATE Pass. In this video we are going to take problems that appeared in GATE 2018 and that were related to thermodynamics. So the first problem, it's very interesting. I have taken it, that is question number 29. Okay, so they have described the system as that in this system G denotes the Gibbs free energy of a binary mixture, NT is the total number of moles present in the system, and mu i's are the chemical potential of species I. Xi is of course the mole fraction of any of the ith component, and they have said that what is the correct variation of G by NT at constant temperature and pressure. Further, they have given in this problem statement that mu I is never equal to 0 and mu 1 is greater than mu 2. Okay, it is based on Euler relation. So let's first derive the Euler relation. Okay, so let's consider a homogeneous system. Okay, so if I have this homogeneous system, what I am doing is I am defining first a system of volume V. Okay, now let's say I define a bigger system, a larger system. Okay, and it has a volume which is V plus dV. Okay, so inside this one it has a volume V. In the outside system it is larger than the inside system and it has a volume of V plus dV. Okay, now we all know this equation. This is your fundamental relation or your Gibbs equation, which relates du is equal to TdS minus PdV plus mu dN. We have already seen this equation quite a number of times. Okay, since this is a homogeneous system, so I can define the small u, that is equal to U by V. Okay, U is your internal energy, S is your entropy, V is the volume, and N are the number of moles. Okay, so now this is a homogeneous system, so I can define my small u, that is equal to U by V. I am defining my small s as S by V, and I am defining rho, that is the density, that is equal to N by V. Okay, now since this is a homogeneous system, u, small s and rho, they will be constant throughout. I mean, they will not vary from one point to another in this volume. Okay, so if I take a differential, then I can write this small u dv, that is equal to du. Similarly, I can write ds, that is equal to small s dv, and I can also write dn, that is equal to rho times dv. Okay, now let's put all these values in this equation, and what do you get? Instead of du, I can write small u dv plus small s t times dv minus pdv plus mu rho dv. Okay, now dv's are all there in it. I can cancel it throughout. Okay, and I can write this equation as small u is equal to small s times t minus p plus mu into rho. Okay, now what I am doing is I will multiply this whole equation by volume. Okay, then if I multiply this by volume, what I get is small u times v, that is equal to capital U, small s times v, that is equal to capital S. Okay, and rho times v, that is equal to n. So I get this equation. This is your Euler's equation. Okay, so this was the equation which we have derived for a homogeneous system. Now I will only retain this equation, which is known as your Euler's equation, and then use it to solve this problem. Okay, so let me write it again. So u is equal to st minus pv plus mu n. Now I have already taught you what is Legendre transformation. You know that u minus st plus pv, that is equal to mu n from this equation. Now what is this? From Legendre transformation, you know that this is nothing but G. If you have not gone through my first lecture which I have made in this series, I have talked about Legendre transformation. You can go and see over there. That is in under GATE 2022 thermodynamics. I think it's part 1. Okay, so u minus st plus pv, that is nothing but G. And since you have now two components, so I can expand this term and write mu1 n1 plus mu2 n2. Okay, Now since they have given you G divided by NT, that is the total number of moles. So if I divide this equation by NT, okay, what do I get? G by NT, that is equal to mu1, because number of moles divided by total number of moles, that is equal to your x1 plus mu2 x2. Okay, now you have this equation. Fine. Now we will apply this equation over here. Since they have said that your mu1 and mu2s are never equal to 0, so these two options, they go away. Okay, because never you have a value which will be equal to 0 from this equation. That's what you see, because if your x1 is equal to 1, your x2 is 0, okay, still you have some term, so it will never be equal to 0, right? So these two are wrong. Let's first see this one, okay, or let's see. Okay, so at x1 equal to 0, let's see what happens over here. At x1 equal to 0, your G by NT limit when x1 tends to 0, that is equal to mu2, because x1 tends to 0, x2 will tend to 1, so G by NT will be equal to mu2. Okay, and similarly if I take a limit, let me erase this. In the limiting case, when my x1 tends to 1, okay, then x2 tends to 0, and what I have is G by NT, that is equal to mu1. Okay, so when you have x1 which tends to 1, you have G by NT, that is equal to mu1, and when you have limiting case of x1 tends to 0, your G by NT is equal to mu2. So this is the right answer. Okay, now this one can't be right, that in the limiting case when x1 tends to 0, then you have your G by NT, that is equal to mu2. So this is wrong. Okay, so the second question is question number 50, in which it is given that you have methane in a piston cylinder arrangement and it obeys this PVT relation. Now the values of B, T, V and N are given. Okay, they have asked you to calculate the isobaric rate of change of T with V or volume in degree centigrade per meter cube. Okay, so what you have to find first, let's write it in terms of your symbols. Okay, so rate of change of T, that means del T with V, del V, and it is isobaric, so at constant P. That is the thing you have to find out in degree centigrade per meter cube. Okay, now the only catch over here is that they have given T equal to 500 degrees centigrade. For all your PVT relations, always remember that don't go and put your temperature in degree centigrade over here. You have to use your Kelvin temperature. Okay, even though it looks quite misleading because temperature is given in centigrade, degree centigrade, and they have asked you to calculate this derivative in terms of centigrade, degree centigrade per meter cube. Okay, but don't do this mistake of putting your temperature in degree centigrade in any PVT relation. Okay, always put it in Kelvin. So I have converted my 500 degree centigrade to 773 Kelvin. Now let's first try to evaluate this derivative from this equation. Okay, so I am going to open this equation. What do I get? PV minus NB into P, that is equal to nRT. Okay, now I am going to take this derivative del T by del V, del T by del V at constant P. So I am using del T by del V at constant P. Of course it is multiplied with R, that is equal to, so I have only P over here. Okay, and P is there which is constant, so derivative of this will give you 0. Okay, so you are left with only P. Now del T by del V at constant P, that is equal to P by nR. But from here, what is your P? So I am going to put my value of P from here. So del T by del V at constant P, that is equal to nRT divided by V minus NV, and this whole thing is divided by nR. My nR in the numerator and denominator gets cancelled, so I am left with T divided by V minus NB. Okay. Now put your values. T as 773, V as 5 minus N is 100 and multiply it with B. So it will be multiplied by 0.029. Okay. So it will be multiplied with 100. So it is 2.9. So do that and do the calculations. That will be equal to 368.9 Kelvin per meter cube. Okay. Now they have asked you to calculate it in degree centigrade. You have got the answer in your Kelvin, but remember one thing, delta T in Kelvin, that is equal to your delta T in degree centigrade. So delta T on both the scales, they are same. So since I am calculating delta T by delta V essentially over here, so equally well I can write that 368.9 degree centigrade per meter cube. Okay, so this is the answer which is given in the key, and don't make the mistake of putting 500 over here. Okay, convert it into Kelvin. I am emphasizing it again and again because this is the only mistake which you can do. Otherwise your problem is very simple. Okay, so this the last problem which we are going to take in this video is question number 14. Okay, so you consider the following properties and you have to tell which of them are intensive properties. Okay, so you all know that temperature and pressure, they are intensive properties that they do not depend on the extent of the system. So you take either 1 mole of a system or 2 mole of a system. Okay, the temperature and pressure, it remains constant. So temperature is your intensive property. Let's see about specific gravity. Specific gravity, that is defined as the density of the substance divided by the density of water. Now what is density? So you are dividing one extensive property by another. When you divide one extensive property by another, then you end up with a intensive property. Okay, so to start with, density is a intensive property. When you divide it further to get this specific gravity, you divide it by the density of water, which is again now your intensive property. So what you get is that your specific gravity, it comes out to be an intensive property. So this one is also correct. Let's see what is chemical potential. So how do you define chemical potential? That is defined as del G by del N. Okay, when you keep temperature, pressure constant and you keep all N constant, Nj constant, where J is not equal to I. That is how you define your chemical potential. Okay, in this case your G, that is the Gibbs free energy, it depends on the extent of the system. So basically it is your G is your extensive property, but since you are dividing it with number of moles, which is again it gives you the size of the system. So it is again, what is it? It is a extensive property. So when you divide your extensive property by another extensive property, then what you get is an intensive property. So again, this is your intensive property. So my chemical potential, it is again an intensive property. It does not depend on the size of the system. Okay. Now volume. Volume, of course, if you have a larger system, okay, your volume will be larger. Okay, so volume, of course, that is an extensive property. However, if I had divided this volume by number of moles, so to get your molar volume, or if I had divided this volume by let's say mass, then you could have got specific volume. In that case, your volume, like the molar volume or specific volume, it would have been intensive variable, but right now they have given only volume, so this is a extensive property. Let's see which of the option gives you P, Q and R. That is option C. So option C is correct. So this was a very straightforward problem, appeared only for 1 point. It's very simple. So that's all for 2018. So what you will observe is that in 2018 they have asked you only 3 questions based on thermodynamics. One of them is very simple. One was a little tricky, which involved Euler's equation, and the third one was straightforward, except that you should keep in mind that you don't have to put your temperature in your PVT relation in terms of degree centigrade. Always try to convert it into Kelvin. Okay, so these 3 were the problems. In next video I am going to take problems from 2017.